Good morning. Today, I'd like to talk about the fact that just from the metric tensor, you can find certain constants of motion along geodesics. In particular, I want to look at the lower component version of the 4 momentum. I'm going to assume that I have a material particle so that I can use the proper time as the parameter. So dot here means derivative with respect to proper time of the person moving along the path. I want to look at the derivative of this with respect to proper time. If I were interested in looking at photons instead, I can still use the tangent vector, but I'll be unable to use proper time for the parameter since a photon doesn't have any proper time. Presuming that the mass, the rest mass, of the particle involved is constant, when I look at the derivative of p alpha, I am looking at the derivative of the constant times. In order to get the quantity inside the brackets, I just did the product rule here. This factor bears some looking at. I'm going to express it in terms of partial derivatives of the metric tensor with respect to coordinates and other things. This term is where the geodesic business is going to come in. By the ordinary chain rule, I can replace the derivative of g alpha beta with respect to lambda by the derivative of the metric component with respect to x number gamma times the derivative of x number gamma with respect to the parameter. Since I'm moving along a geodesic, the second derivative of x number beta is given by negative Christoffel beta mu nu x dot mu x dot nu. I'm going to relabel that first term. Here, the derivatives are taken from x mu and x nu. Here, from x gamma and x beta. I'm going to rename gamma to mu and beta to nu. There is no naming conflict because in this first term there is no mu and nu as it stands. Of course, because of the inverse matrix business, the sum over beta of g alpha beta downstairs, g beta sigma upstairs, is the sigma alpha entry in the identity matrix, the Kronecker delta sigma alpha. This is a sum over sigma, but I'm going to get a non-zero term only when sigma is equal to alpha. If you'll notice, g alpha nu and g nu alpha are the same because the metric is a symmetric tensor. Alpha on the inside, alpha on the inside, mu, index of summation, mu, index of summation, nu, index of summation. This number and that number are the same except for the factor of 1/2. After using that to combine these two terms, another observation is worth making. In this first term, alpha shows up as one of the indexes on the metric tensor and does so there as well. The second index on the metric is an index of summation showing up as an index on an x dot symbol. The mu is an index of summation, also shows up as the index on one of the x dot quantities. Look at the second term. Alpha is one of the indexes on the metric. Mu is likewise an index of summation. Nu, likewise, is an index of summation. If I wanted to, in this middle term, I could interchange mu and nu. The quantities that I am multiplying together and adding up in the second term are the same as those in the first term. So this term and that term cancel each other out. What we have figured out is this. If you're moving along a geodesic for a material particle, then the derivative of p sub alpha with respect to proper time is just given by this expression. By itself, this doesn't give me a very impressive result, but it leads to something that's extremely convenient for us. Suppose that you had some index alpha, and no component of the metric tensor depended on the coordinate number alpha, on x alpha, that is. If that's the case, then all of these partial derivatives are zero. That says that the derivative of p sub alpha with respect to tau must be zero. That means if the path we're following is a geodesic, then p sub alpha is a constant. One of the components of the one-form version of the four momentum does not change at all as you travel along the geodesic. This is going to be extremely convenient for us. In a little bit, we will be able to get the equations of motion, the equations of the geodesics, in a way that's very similar to what Isaac Newton would do. Coming up next, we will apply this to a simplified approximate toy model, and then we'll move on from there. Until then, I hope everyone has a good day, and I'll talk to you again soon.